Hey there, ever wondered why some metals seem to have all the fun reacting with just about everything, while others just don't? Why a gold ring can last for centuries, looking brand new, but an iron nail starts to rust if you just look at it funny? Well, you've come to the right place. Today, we're cracking the code on the Reactivity series, which is pretty much the ultimate guide to understanding why metals behave the way they do. So, here's our game plan. First, we're going to look at the Metal League table, the official power rankings. Then, we'll see how we actually rank these competitors. After that, it's time for the main event, the Great Metal Swap. We'll also cover how this all helps us in the real world with fighting off rust. And finally, we'll uncover the secret of redox, the chemical rule that makes all of this work. Let's start with a really simple question. You've got a gold ring, right? It stays shiny forever. But an iron gate? After a few years out in the rain, it's a flaky reddish-brown mess. So what gives? The answer is all about one simple but incredibly powerful idea. When it comes to chemistry, not all metals are created equal. Some are just way more eager to react than others. And that brings us to our first stop, the Metal League table. Honestly, the best way to think about this is like a power ranking for a sports league. It tells us, at a glance, which metals are the super aggressive champions and which ones are, well, a bit more chilled out. And here it is, the league table in all its glory. Right at the very top, we have the undisputed heavyweights, like potassium. This stuff is incredibly reactive. As we go down the list through metals you know like magnesium, zinc, and iron, you can see they get progressively less reactive. And then, way down at the bottom, we've got our super stable, unreactive metals like silver and gold. This one list is the key to predicting tons of chemical reactions, and it all boils down to how willing each metal is to give away its electrons. So how do chemists actually figure this out? I mean, they don't just guess, right? Of course not. They basically put all the metals through a series of chemical challenges to see how they stack up against each other. Let's see how that works. One of the classic tests is just seeing how a metal reacts with plain old cold water. And you can see the difference immediately. You take potassium, our champion from the top of the table, and it goes absolutely wild. It reacts so fast that the hydrogen gas it produces actually bursts into a lilac-colored flame. Whoa! Calcium is a bit more chilled out. It reacts, sure, you get some gentle bubbling, and it gets a bit warm. And then you have magnesium. It pretty much does nothing. Maybe a few bubbles will cling to the surface, but that's it. These totally different reactions are all the evidence we need to place them in the series. This gives us a really simple, step-by-step method to figure out where any unknown metal fits in. First, try it in cold water. If it goes nuts, you know it's a top-tier metal. If not much happens, you move on to level 2. Try it in some dilute acid. If it fizzes up now, you know it's somewhere in the middle of the series. And if there's still no reaction, well then you've got one of the unreactive guys from the bottom of the table, like copper. All right, now let's see this league table in action. This is where things get really dramatic, with something called displacement reactions. This is literally where a more reactive metal can just march in and kick a less reactive metal right out of its compound. So just think of a displacement reaction as a chemical competition. The rule is dead simple. The more reactive metal wins, and the less reactive metal gets displaced, or, kicked out. This is the absolute golden rule. It's not a sometimes thing, it's an always thing. If you put a more reactive metal into a solution with a less reactive metal's compound, the stronger one will take over. Every single time. The league table doesn't lie. Let's watch a classic matchup, magnesium versus copper. If you mix magnesium powder with black copper oxide and heat them up, you get a seriously spectacular reaction. We're talking sparks, a blindingly bright flash of light. It's awesome. But why? Well, just look at the series. Magnesium is way higher up than copper. It's much more reactive, so it just strolls in, steals the oxygen from the copper, and leaves pure copper behind. Magnesium wins. Okay, so this is about more than just making sparks fly in a lab. The Reactivity series has some incredibly important uses in the real world. Let's see how it helps us fight one of chemistry's biggest villains, rust. The recipe for rust is almost ridiculously simple. For iron or steel to start rusting, it just needs two things to be there: oxygen from the air and water. That's it. If you have iron, oxygen, and water together, that familiar reddish-brown flaky stuff is pretty much inevitable. So how do we stop it? Well, the simple way is just to create a barrier. You can paint it, oil it, or coat it in plastic to keep the air and water out. But the really clever methods use the Reactivity series against itself. Galvanizing, for example, means coating the iron with zinc. Now check the table. Zinc is more reactive than iron. So if the coating gets scratched, the zinc corrodes first, protecting the iron underneath. It sacrifices itself. Sacrificial protection is just that idea on a massive scale. On a steel ship, they'll literally bolt huge blocks of zinc or magnesium to the hull. These blocks corrode away over time, sacrificing themselves to save the ship. So cool. Okay, for our last section, let's pull back the curtain. Let's look at the deep, fundamental chemistry that actually explains why all of this works. We need to talk about the secret engine driving everything: redox reactions. Turns out, every single displacement reaction we've looked at is a redox reaction, and the name itself is a huge clue. It's just a mashup of two things that always happen together: reduction and oxidation. You can never ever have one without the other. They're a package deal. Now, there are two ways to define these two processes. The original way was all about oxygen. If a substance gains oxygen, we say it's been oxidized. If it loses oxygen, it's been reduced. That works for our magnesium and copper oxide example. But the bigger, more important definition is all about electrons. Oxidation is loss of electrons, and reduction is gain of electrons. This is the definition that explains everything, even when there's no oxygen involved at all. And for anyone studying for an exam like the IGCSE, you absolutely have to remember this. Here is the magic phrase that will save you: oil rig. Just drill it into your brain. Oil rig. Oxidation is loss, reduction is gain of electrons. So when our reactive magnesium atom kicked out copper, it lost electrons. It was oxidized. And the copper ion gained those electrons to become a neutral copper atom. It was reduced. See? Oil rig. It's that simple. So, we've seen how the reactivity series is built, how it lets us predict winners and losers in chemical reactions, and even how it helps us protect giant ships from turning into rust buckets. Which leaves us with one last big question. Now that you know the rules of the Metal League, how do you think we use this exact same knowledge to do one of the most important jobs there is: pulling valuable metals like iron out of the ground? That's a great question to think about. Thanks for watching.